So now conceptually we have the science of filmmaking is no longer artistic based, it's mathematically based. We have equations, we have angles, we have distance over time, all very simple, complex, simple ideas that take complex equations to solve them. And the beauty of it is once you understand what these equations are, you can apply them systematically to find something as simple as length and width in depth in a film of view, where before all you had was length and width.
I'm Alan Adams, Chief Structural Engineer for Bentley Systems Incorporated. Early in my career I worked for a structural engineering firm where I designed buildings, hotels, offices, parking garages. During that time we founded a software company to design the skeleton of buildings. It is estimated that over half of the steel buildings built in the U.S. in the past several years were designed using our software. The Vista Courthouse, Vista City Center, and the San Marcos City Center are three local examples, among others, of such projects. It is common practice to build prototypes of new products, toys, tools, even cars, to test and verify through actual use the functionality and correctness of the design and manufacture of the product before that product goes into mass production. If the prototype is found to be flawed, it is discarded and a new, improved prototype created. This process is repeated until the design is acceptable. It is, however, impractical to build prototypes of buildings. Each building is unique. You have to get the design right the first time. Thus, it is necessary to create mathematical models of the building structure and mathematical representations of the forces that may act on the building. A virtual building with virtual forces acting on it. Using the seismographic data from earthquakes, geotechnical engineers construct a response spectrum curve, a mathematical representation of earthquake ground motions. These equations are implemented in the software to represent the earthquake forces to which a building may be subjected. Similarly, equations are developed and implemented to represent wind forces, including hurricanes. Consider the beams and columns that make up the skeleton of the building. These members are represented by matrices and arrays of coordinates, angles, lengths, and material properties, all part of the math language. Through matrix algebra, the interaction of the forces in the support skeleton and the interaction of the members with each other can be determined, performed of course, by the computer, since those matrices may have tens of thousands of entries. Geometry is used extensively to determine member and force relationships and orientations. Equations representing the strength of structural shapes, such as a steel I-beam or a round pipe section, are programmed and used to determine the capacity and adequacy of the design being investigated. Through the use of mathematics, the engineer is assisted in his task of designing safe and reliable buildings, warned when they are not, and given the ability to correct any defects or shortcomings, all before the building is actually constructed. Mathematics, practically applied, is the language of much of what we do as structural engineers.
So whether we're talking about how much money flows in and out of our bank account on a monthly basis, or how long it's going to take to pay off that car once you add up the cost of the car, the tax, the licensing, and if you take out the loan, the additional interest you're paying on top of that. Whether we're talking about how to build a building from the bottom up, how to make sure that the footings are right for the type of soil we're dealing with, make sure that all the bracings are right, make sure that it can handle the earthquakes that are prevalent in the area, or the winds and the rain, all of the other elements. Whether we're talking about doing three-dimensional motion capture and collecting hundreds of thousands or even millions of pieces of information, then organizing them so we can bring an animated object to life. All these things and so many more are dependent upon the mathematics language. As we go through this course, we're going to stop and talk about how all of these different pieces of information get used in the real world. And the benefit you get is that by learning the math, you'll be able to describe many more things in your life, and it'll help you solve many problems.